Good morning, everyone. It's really a great honor for me to be here today and present our paper. So fortunately in Austria, we are better in building tunnels than keeping flight times accurate. So I've just arrived literally 2 minutes ago. What I'm going to talk to you today is about exactly bridging the gap between technology and acceptance by the client. And as a university, so I'm head of an institute at Graz University of Technology, I think we're in the perfect role in making proof of concepts, making case studies, and support technology becoming state-of-the-art. And this is what this talk is about. So we're going to take a look at a large tunnel construction project in Austria, and I would like to show you what we do there, especially with distributed fiber optic sensing. So currently, we are responsible for the fiber optic monitoring of 6 different tunnels. So 4 are train tunnels currently under construction. 2 of them are highway tunnels that are already existing. What I would like to talk to you today is the Semmering Base Tunnel. So this is one of the largest construction projects that we currently run in Austria. And what we're talking about here is a base tunnel with a length of 27.3 kilometers, 2 tubes, cross passages every 500 meters. And what's interesting is in order to reduce construction time, we don't build from both ends, we build from one end and from 3 intermediate construction sites. And the whole tunnel is scheduled to be finished in 2026. And on all of these 4 construction sites, we use distributed fiber optic sensing, and I would like to show you that you can do much more than just monitoring the tunnel lining. But first of all, we're going to take a look at monitoring of the tunnel lining. So we make a journey from the north portal in Gloggnitz down through the different construction sites of the tunnel. So what do you see here? This is the north portal. This is already the bridge where the high-speed rails railway line should go into the tunnel. And what we do here, what the task here is, the monitoring of the tunnel lining in conventional tunneling. So if you're not so familiar with that, so in conventional tunneling, you cut out the top heading first, then the bench and invert. In this case, bench and invert are cut out simultaneously. This is happening a few days after the top heading is being cut out. So you temporarily support the tunnel cross-section by using steel girders, by using shotcrete, maybe anchors, but the whole idea is that the tunnel finds its state of equilibrium again itself. So monitoring is an essential part of this process. So what we do, we monitor the top hanging, bench and invert, and assess the lining behavior. And here you have a feedback cycle. Because of the measurements, you adapt your construction sequence. And adaptation means you change the length of the turnaround. So if you cut out 0.5 meter, 1 meter, you also decide the amount and type of support. So you can see anchors, how many anchors you need and where you're going to place them. You can also change the thickness of the shotcrete layer. So monitoring is required in order to perform this type of construction at all. Conventionally, this is done with geodetic methods. So geodetic methods mean we have 3D displacement measurements. And you can see that pretty nicely when you take a picture with a flash. So what we can see here, all these reflecting points actually bireflex targets. And what you can also see, they are aligned in cross sections. Usually it's 5 to 7 of these targets at every cross section. They are measured manually and are measured once a day. But this measurement only happens when the tunnel section is close to that tunnel face. As the tunnel phase progresses, you thin out the measurement interval and maybe only measure monthly or quarterly these cross sections. So from that perspective, this method is a well-proven method, but it's not really suited for fault zones because you don't have a dense measurement interval. You have only 1 measurement per day. You don't have any idea what's happening in the bench invert section. And you're always in the way, basically, when you perform the measurements because you set up a tripod, you have an instrument, you interrupt the construction process. And due to all these reasons, here, the idea was to use distributed fiber optic sensing, where we place essentially cross-sections with distributed fiber optic sensing cables. We measure temperature and strain at every section. We measure the concrete behavior of the outer shotcrete lining and the inner shotcrete lining. We perform measurements continuously for the first few weeks after construction, close by to the cross-section, and as the tunnel progresses, we connect individual cross-sections and have a central measurements location further outside of the tunnel. The question is always, fiber optics, does that work? Yeah? Does the fiber survive that process? And also, this tunnel is supposed to have a design lifetime of 150 years. So does that also work for the next 150 years? Shotcreting is a rather harsh procedure. You have that sprayed concrete, which is put with high pressure onto the tunnel walls, and all what you have to install here has to survive this process. What we are using here the fiber optic sensing cables in a metal tube and align them along the steel grids. So you can see here in blue the strain sensing cable, in red the temperature sensing cable. All of these cables are then connected in one connection box with the leading cable, so multi-core leading cable, which actually leads then back to the measurements location. With all the installation we've made so far, so shotcreting was never the problem. So all of these installations survived the application of shotcrete. We measure with a fiber optic cable. So in the end, we get the measurement information at kilometer, point, whatever. All along that fiber, we do have this information. So you have to relate that into a spatial location, so in an X, Y, Z location, in the best case in a tunnel coordinate system. In order to do that, we scan the tunnel cross-section and its surroundings, and then we perform total station measurements where we measure reflectorless to the sensing cables. So actually what you can see here in blue and in red are the fiber optic cables of the outer and the inner lining of the shotcrete. So for every fiber meter, we know exactly where it is within the tunnel. And this also helps for the interpretation. In order to make technology acceptable, you have to present the results in a way that the usual client understands it. So what we're doing, for instance, we make plots like this. So we display the development of the strain along the cross-section in an animated way. So we can see here, this is the cross-section where we've installed the fiber. You can also see then how the tunnel excavation progresses. So first, we do see the shortening along the top heading. The bench invert aren't cut out yet. Now they are cut out. They're also showing shortening, which also decreases, or the speed of it decreases with time. So on one hand, we can display the strain distribution spatially, but we can also take a look how this strain changes with time. Not so easy to see in this plot, but it's much easier to see when you take now, for instance, timelines of a few points. What we do see as a typical behavior in conventional tunneling, we see first a rather strong strain development, which then slowly decreases. What we can also see, as soon as we cut out the bench and invert, we also see again an acceleration of the top heading, and especially in this case, a change of the behavior of the right shoulder. This is now permanent monitoring for a few weeks. And very often in tunneling, we have projects where we have to monitor the behavior permanently right after construction for a few weeks, but then in the long term, it's maybe quarterly, monthly, half a year. And in case if we see something in long-term measurements, we then again perform continuous measurements. So just a graph of the long-term measurements. I just plotted the measurements also that we did last week. So actually it's a normal behavior. It's slowly stabilizing, so nothing special is there, and we need no special actions for this cross-section. I'm coming from the monitoring side. For me, this is always boring when everything works as expected, but of course the client here is pretty happy with those results as well. Now we go to the next access point. This is in Göstritz. This is, from my point of view, the most interesting or most challenging installation, because here we have tunnel construction, but we have first an access tunnel with a length of more than 1 kilometer, then 2 shafts, which are both more than 200 meters deep. And here the question is, how do the shafts perform in the long term? And in case if the behavior is not as expected, you would have to stop the construction, and you also have, obviously, to guarantee the support again, for instance, by applying extra additional anchors to that. Again, similar, like it looks like a flipped picture from the tunnel tubes, but believe me, installation is something totally different when you make it done in a vertical shaft and not along the tunnel tube. Because if someone loses a hammer 150 meters in front of you, you do not care. If someone loses a hammer 150 meters above you, you definitely do care. So it's really, a very challenging environment. Again, similar principle. We have here those cross sections. These were selected because we have some geological fault zones in these areas. We have connection boxes, and from these boxes, there are multi-core fibers going up to a central location where we actually do perform the measurements. So this is here the, one of the shafts. Here you can see then the leading cables, and this is an measurement box. And I would also like to share you one typical result you get from a Brignon distributed measurement. This is the initial measurement made down at the shaft. So we have here the strain sensing cable, then the splice, the temperature sensing cable, both of them for the outer concrete layer, and we also embedded them in the inner concrete layer. So again, the same here, the strain sensing cable, and then the temperature sensing cable. And then this is here the end at the connection box, the same end at the connection box, and from there it goes up to the shaft, to the top of the shaft. Obviously, we can plot the results in a similar way. And again, in this area here, we have behavior as expected, so nothing is really to do. At the moment, no special support needed. When we go one step further, so one step further to the south, this is the access point Göstritz. Here we have two shafts, 400 meters deep, and then the tubes underneath. So we could, again, talk about shaft monitoring. But here there's also one other very special application for monitoring. We are building a tunnel with 4 different construction sites. And here, one requirement from the legal point of view was that from these 3 intermediate construction sites, all the material has to stay in this area. So it was not allowed to move the material out of the area. So you have now here 3 access points. You have construction on 2 tubes on every side. So in the end, you have 12 construction sites running in parallel and just 1 disposal site. And disposal site is located here, and this has to work all the time. Because if this disposal site is not working, you cannot continue the tunnel construction. So the question is, how does such a disposal site look like? We're in an alpine area, so it's pretty simple. You select the valley, and you fill up the valley. So this is the valley in its initial state. This was the valley a little bit later. What you can see, all these trees are being cut away, and the material will fill up the whole valley here. One challenge here was, like usual in such a valley, you do have a little river at the bottom of the valley. And there was one precondition that this river has to survive. So from a technical point of view, the easiest thing would be to put it in a massive tube. No, the river had to survive, and it was allowed to move it, but only once. So you got this river in its original bed. You shift it up 50 meters. That's the new riverbed. And this, let's say, V-shaped valley, after the whole thing is being filled up, looks more like a kind of a U-shaped valley. But the question is here now really the stability of this structure. If this structure is not stable, you cannot use the whole disposal site, and you cannot continue with tunnel construction. Okay, so just to give you an idea, this wall was made with reinforced earth. So we have here geogrids every half a meter. And the question was now, how does this structure behave? How does it behave during the construction phase, and how does it behave in the long term? And of interest was here absolute deformation, so rigid body motion, tilt changes, but also the internal strain of these geogrids, because all of these have a strain limit, and of interest was how close are we to this strain limit. Like with all those structures or all these projects, these are not just research projects anymore. There's actually a safety plan behind it. And if we see something which shouldn't be there, there's some counter actions planned. And in this case, it would have been some concrete elements which would have been re-anchored into the ground. So how do we do the monitoring? Here we use a combination of conventional monitoring. So we have here classical geodetic measurements to points on the surface of the structure. So from these measurements, we get highly accurate the absolute movement of that point, and we can also determine possible tilt changes. And internally, we do measure, again, with a distributed fiber optic system. The whole structure looks like this. Here of interest is this access ramp, which is about 25 meters high, inclination of 60 degrees. So we have one central measurement container location, and then a loop of more than 2 kilometers where the fibers always go inside of the reinforced earth, out again, inside, out again, and so forth. So from one location, we can measure the whole monitoring installation. This is the way it looked like after it has been finished. Now we can take a look inside, what's actually inside, and maybe we're going to take a look at profile 2, the second level here. And what we do see here is we do see an increase of strain during the construction phase. It's not homogeneous, so we have in this section less strain in the front, more strain in the back. The strain reaches levels of a little bit more than 1%. Also continue after the construction ended, but then they start to stabilize. So from that point of view, we can say question solved, structure is stable, so no need to monitor anymore. What we do have here, we have here a 10-year contract to monitor and also to detect possible changes during the lifetime of the structure. Just to give you an impression, this is a picture taken in 2016. So the reinforced earth was finished, and also filling up of the disposal site already started. That's a picture from last month. Same location, and you can see that the disposal site is more than 50% full already. So all of this is already being filled up with the tunnel excavation material. So what's happening in the long term? There shouldn't be anything happening, but what we do see here, for instance, this is a timeline of one of the levels of the first cross-section. We do see the deformations in the beginning, then almost no deformation, and then at one point in time, we do see a jump in the time series, which seems to stabilize again. So what is happening here? Could have been there's some water ingress on the back side, could have been some other change of the way the structure is being used. And actually what's happening exactly between here and here, you can see on these pictures. So that's the situation beforehand, that's the situation after, or in between. So what we do see here, the original idea was that the trucks drive this road, make this narrow turn, and then go further up. Then they wanted to use heavier trucks, which weren't able to manage this curve. So what you do, you just fill up this section. So you get extra load here. We got all the material here. And what you can see here, now they don't make the initial track anymore. Now they actually cut the curve and use trucks which are much heavier than they initially were planned. And the question is here now, how does the structure behave? What we did see that one-time jump, but now it looks like to be stable again. You can see these were the original trucks which they still use, but most of them are now more than 60 tons lorries like this one here. So we do see the change, so the long-term monitoring does make sense. However, it's a non-critical change, and we continue monitoring to see if in the long term there's an impact due to the heavier load that is being transferred over those areas. So we already have shafts, tunnel cross-sections, and a reinforced earth structure. We move now to the most southern part of the tunnel construction site. This is the access point Grautschenhof. A really narrow construction site. Initially, it was never planned to actually start here the tunnel construction, but due to some other problems, they had to relocate an initial planned site to this site here. So you almost have no space. You have a highway nearby. You have two shafts, 100 meters deep, massive caverns underneath, and the two tunnel tubes. Difficult enough, but then you do have one of the main gas pipelines connecting the north of Austria to the south. You can imagine the reaction of the operator of this gas pipeline when the train company said, okay, we are building 2 shafts next to your pipeline. We are digging a few caverns underneath. We have 2 tubes. And by the way, all our construction traffic will just go above your pipeline. So the good thing in this situation, money is then not really the problem. So there had to be some monitoring and permanent monitoring of this pipeline with automatic alarming and warning. And what do you do when you really have an impact on a pipeline? So first of all, you have to stop the operation of the pipeline, and then you have to excavate the tunnel construction site and also close down the highway. So here we're really in a very sensitive situation. We have different warning and alarming levels. So warning level just means special inspection and a close look at it, but alarm level really means turn off the gas pipeline. And if you really cut off the gas for 1/8 of the population of Austria, you really better be sure that it's needed. Okay, monitoring. You would say, okay, we can do that with conventional methods. So conventionally would be fully automatic measurements with a total station, for instance. This can easily be done. It's a well-proven technique, also in urban tunneling. And what you do see here is the layout of all the monitoring points. You can see here monitoring points in the tunnel. We can see here the 2 shafts. And actually, this is the track where the pipeline is underneath. So this is exactly that road where the construction trucks are going above that pipeline. This is the way it looked like in February 2016. You have the highway, and these are load distribution plates just covering the pipeline. We have here the location where the 2 shafts are located now. So in this situation, it's no problem to perform permanent measurements of those plates with a total station. However, it's impossible to do it here. You have here somewhere those load distribution plates. You have the trucks permanently passing by. So you cannot perform conventional geodetic methods in a permanent sense. You can do that epoch-wise by performing maybe manual measurements. But if you set up some total stations, you never manage to have a line of sight to all the targets that you are interested in. And this was here the motivation why we were looking for something to monitor directly the pipeline itself, not just what's happening above of the pipeline, but really the pipeline itself. So we therefore applied 3 lines of fiber optic cables. All of them had several fibers inside to have some redundancy in that system. Overall, the sections were rather short, just 350 meters, but we installed about 2.5 kilometers of cable with all the redundancy we have and also with the leading cable to the monitoring location. They are located at 9 o'clock, 12 o'clock, and 3 o'clock. And by having that layout, we can, on one hand, calculate the horizontal curvature by taking a look at these 2 values, and also by taking a look at this reading and the average of these 2 sensors, we can also calculate the vertical curvature. Because here we do have threshold values for the longitudinal strain, but especially threshold values for curvature, especially vertical curvature. Because of an unexpected settlement, we could have a very high vertical curvature, which could cause damage to the pipeline. This is fully automatic, so here we really have an instrument running permanently 24/7, and this since almost 3 years now. We have, in this case, a combined BO-DDR and BO-DDA instrument. We are running it in the A mode, but in case if really one fiber breaks, we can switch to the R mode. We analyze that fully automatically and also send out automatic reports, also with some pictures and numbers. And again, important for the people who inspect or who are on site, when we see something, we also quote the 3D location of that position so that people can go there and really stake out where we do see some excessive curvature changes or length changes. The difficulty that I have with this presentation is that I'm almost not allowed to show any results. So I think in the nature of projects like this, But what I can show you a little bit is, this is, for instance, one of the straight sections. So we have subdivided into several sections for which we provide the results. So this is the straight section. You can see here our warning level is at 230 microstrain, alarming is at 460 microstrain. And in this section, we see some small changes, but nothing in the warning or alarm level. What you can also see here, the construction site ends here and here, and there's a little road here. And we just happened that also we measure also a little bit on this side, and suddenly you see something, and someone dig the trench, which was not really communicated because it's not on the construction site, but just nearby. And due to that operation, we did see at that location a massive increase of the strain of the vertical sensor, which also stabilized. So very often we did see something that we did call up the people on site. We do see something, maybe you should take a look what's actually happening on it. But in the end, everything is running fine, and we had not to shut down the pipeline so far. We're sometimes in warning area. Usually this was because someone or some trucks crossed at some sections where they were not allowed to. Okay, so what I wanted to give you just a short overview, what you can do with distributed fiber optic sensing at tunnel construction sites. What I wanted to show you is that we don't see the fiber optic sensors as a completely replacement of all other sensors. It's not like that every new technology replaces all the old technology. We see it more as a complementary technique to existing techniques. What we have proven with our project is that this technology can withstand the harsh environment on tunnel construction sites. It enables the strain measurements at locations which are usually not accessible with geodetic methods, like the bench and invert section. We can measure without interruption of the tunnel construction. We interrupt it when we install the sensors, but for the measurements, we do not have to go to the measurement location anymore. And due to the distributed nature, we can localize where a problem does occur. What I wanted to show, it's not just possible to monitor the tunnel linings, but also other critical infrastructure and projects in nearby. And our goal is, of course, to increase the safety of the workers on one hand, but also the efficiency of the construction. What you do see here, this is the tunnel boring machine, which is just starting to work now, 400 meters down the shafts in Longsgraben. And we also had already projects with tunnel lining segments at another tunnel, which we also would like to do at this tunnel here as well. And so I'm here making the presentation. There are many co-authors for this paper, but also for the installation of this work. This only does work when you have highly competent and motivated team members, which are able to climb, which are not afraid of water coming down a shaft, which have to be creative in order to protect the installation. So I really am very proud of the team that I do have. And if you also find this interesting, we are currently also looking for some new people. So maybe you could talk after, come to me in the break. I'm really glad that I made it on time here. And I also thank you very much for your attention. Thank you.